Okay, hi guys. Okay, I thought I would take the opportunity of this lovely evening to come and explain my favorite topic in the year 12 physics syllabus, which is, oh wait, what is the topic called? Internal resistance. Okay, internal resistance. Sorry it's a bit dark at the moment, it's like 7 p.m, but if you actually come and learn with me, a lot of my classes are in the evening, so this will probably be what it's quite similar to what it's actually like. Okay, or if you already learned with me, you'll know that it is this kind of vibe. Okay, so I'm drawing a graph right now. Actually, maybe I shouldn't be drawing a graph right now, but I'll just draw the axes here for now. Anyways, I don't know who's watching this, so if you are already in year 13 and you have already learned this, there's a topic called internal resistance, or like subtopic really, which is part of the electricity topic. And then you might remember there's this diagram where there's the battery, the internal resistance R. If you're younger than year 13, honestly you can probably understand this. So I'm just gonna draw a circuit, like the relevant circuit for this, the concept that we're gonna talk about today. This is my favorite topic because back then, right, I was in it like year 12 or something, and I really didn't understand this at all. And so I spent like about a weekend trying to understand this graph that I'm gonna draw later on, or like just the general idea, like just the general formula. Basically, I didn't get any of it, but it is actually not that hard, and I will explain it today. Kind of struggling with this drawing. Okay. I mean, there's a lot of students that might end up like just remembering stuff for the exam. I would suggest, if you can, try to understand like where everything comes from, because that gives you like a much like longer term understanding, and it's also a lot more interesting, and you get a better score in the end anyways because you actually like truly understand it. But in a lot of cases, like if you come and get tutored very close to the exam, you can't really go that deeply into this kind of thing, so you just kind of have to like memorize the most basic stuff. But anyways, I'm gonna explain it. Okay, so the idea is, right, okay, this is a circuit, very simple, and then you have a battery here which has something which is called internal resistance, which is the name of this topic. And internal resistance is the resistance of the battery itself, like, because batteries are not like perfect, they lose energy through heat and that kind of thing, because internally it's made of like wire. Actually, I don't know what they're made up of, but like it loses energy basically if a current goes around this circuit. So it has something called an internal resistance of its own. And so this is the battery here, this is the internal resistance, and then this is the external resistance, or like the resistance outside of the battery, which could just be like a light bulb or something. But we're gonna call the internal resistance small r and the external resistance large R. And aside from that, I put an ammeter there, which measures the current, and a voltmeter, which is connected around the battery. Okay. So now that we have this, right, there's a relationship between all of these things. There's one other thing here actually, which is called E. And E is like the e.m.f, electromotive force, which is like the kind of like the energy of the battery before thinking about its internal resistance, basically. So there's a relationship between E, R, I, and large R, or sometimes like E, I, R, small r, and V, which really I didn't get at all in the beginning, but it is V is equal to Wait, what is it? V is equal to E minus IR. Okay, so the E is like the EMF here. V is the, you call this like the terminal PD. Sorry, there's no space to put my face. Okay, there, it can go there. V is the terminal PD. E is the EMF of the cell. I is the current in the circuit, so it's just the same all around, and then R is the internal resistance. So basically, if you look at this formula in general, it's kind of saying that like the actual voltage, like the energy that goes to the resistance outside of the cell, is slightly less than the EMF from the battery. It's like the EMF of the battery minus a small bit, because this is like the energy that's lost to the battery. You know, now that I'm saying it like this, I'm like, why didn't I understand it in the past? I don't know if this is making that much sense to you at the moment, but actually I feel like I already finished explaining it. The energy that the resistance outside gets is the EMF of the, it's like the original energy of the cell minus the energy that like is lost to the internal resistance. So imagine like an electron going around, conventional current direction is in this direction, so the electron is actually going in this direction. That's not really that important. So an electron goes around, like when it goes through this internal resistance, it gives off a bit of energy, and then it continues going around this circuit, and when it gets to this part, it gives off another larger bit of energy, basically. That's kind of the idea. And if we add those two bits of energy up together, that's like the total energy that a charge has going around the circuit. Yes. Okay. So, the thing that used to confuse me was that there was a graph that came with this. And, you know, I'm really gonna struggle here with like because there is not enough space to put everything. Can I make this smaller? Let me zoom out on everything. Okay. If we draw a graph of V against I, we're gonna get a line, and the line is not what you would expect, basically, because you might be used to the graph of V against I, which goes like this. V, no, not like this. It goes through the origin. So V is proportional to I because V is equal to IR. But then for this graph of the internal resistance, when we draw a graph of V against I, where V is the terminal PD, or like the voltage across here, right, this V, we get a graph that looks instead like this. And this used to confuse me so much. Okay, so what is happening here? There's also a bunch of other things that we can label on this diagram, but first let's analyze it using maths. So the equation here is V is equal to E minus IR. No, sorry, not large R, small r. Very important. Okay. And so what we have here is V being the y-axis and I being the x-axis. And so we can basically compare this to the normal equation of a straight line, which is y is equal to mx plus c. Y is equal to c plus, okay, no, this isn't gonna work. Let me rewrite it in the form y is equal to e.m.f plus c. Y, because v is y, right, is equal to m is minus r, x is I, plus c, which is e. Can you guys see where it comes, like why it goes from the top line to the bottom line? So this is the y, this is the m, this is the x, and then this is the c. So when you do this, and then when you compare the top line and the bottom line, you can see that the gradient of this line is minus r. So m is equal to minus r. And then the C or the y-intercept is E, so this is E. And then, this point is 0, by the way, it's like 0, 0. And then here is something which is called Imax, which is the maximum possible current that you can get in this circuit. Okay, even though that might make sense mathematically, that might not yet make sense as like, you know, in real life. So I'm gonna explain some more. Okay, first of all, let's look at the idea of like why is E here. At this point, right, we have no current going through the circuit at all. Imagine there's no current going through the circuit at all. And basically what you're doing is you're measuring the voltage directly across the cell. And so what you're doing is like there's no current going through it, so there's no energy being lost. And so basically you're connecting the two ends of the voltmeter across the battery, and it's just measuring the original, or like the e.m.f. of the cell E before any energy is lost at all. So that's why here is E. And then let's look at this point here, Imax, and see why it's Imax. So at that point, the voltage is 0. Voltage is 0, and we have maximum current. You know, actually I haven't thought about this for a while. When do we have maximum current? Oh, okay, I got it. Okay, that took a while. Okay, so let's think about like what this graph is actually kind of describing and like what's happening as we go along the axes, right? So as we go from left to right, what's happening is the current is increasing. We're like increasing this Imax here, and we're decreasing this terminal potential difference here. And so what we're actually doing is the current is no, wait, why am I saying decreasing? The current is increasing as you go from left to right, as in like as you go along this axis, you know. The current is increasing, and the only way you can make the current increase is to change this external resistance here. So what's happening as you go along this axes is that you're making this external resistance smaller and smaller. But at a certain point, when you don't have any resistance there at all, then it just becomes a circuit which is just going, imagine like there was no resistor here, then it would just basically be a circuit with one resistor, which is the internal resistance here, small r. And so that at that point, right, that's when you get the maximum current, because as the resistance decreases, current increases, because current and voltage are inversely proportional. I don't know if this is getting confusing, but essentially the idea is as you go along that and as you're decreasing the resistance, you get to a certain point where you get to the maximum current, which is when there is no resistance here at all, like there's nothing here, and then it's just the maximum current is due to like is when the current is going through the circuit and there's only one internal resistance. And so you can actually always have this, like find the value for this Imax, because that's when V is equal to 0, and that's also when you have only this E and only this R. So I would be V over R, right, usually. And in that case, that's confusing. No, it's not V over R. I mean, like in general, it's voltage over resistance. And so it would be large E over small r. Always. You can remember that to be fast. I know, I feel like this is confusing. If this was real, like if this was a real class, I would ask if you guys had any questions, but because it's just me talking, I will not. So hopefully that makes sense so far. Like from the formula, if you put V is equal to 0, you can also see that I rearranges to be E over R. So that's another way you can get to this answer. But like thinking about the circuit, that's how you get to it. Last thing is, why is the gradient equal to minus R? Okay, this is, I think it's quite fun. quite fun, only for me maybe, but hopefully okay for you as well. Okay, so the idea is, right, what is gradient in general? Gradient is rise over run, or like it's like the rate of change of something. So this gradient here is how much the voltage changes, how much this voltage changes as we go across to the right by 1. Like as you know, I really need to like write more, but I have no space at all. Is that still visible? I hope that it's still okay. What was I saying? Okay, the gradient is minus r. You can already see that from like comparing it to the y is equal to mx plus c form. But the other thing is, like, the way to think about the gradient, right, is the rate of change. So it's like how much v changes, and v is like the terminal PD here, as you increase I by 1 amp. So it's like as you go across 1 here, how much, what is this change here? And we already know it's minus r. So like V decreases by minus r. So why does V change, like why does V change by minus R as you increase the current by 1 amp? If you, okay, let's do it by thinking about the circuit, right? Let's say you did increase the current by 1 amp, that would be like by like decreasing this resistance basically. What you have is like 1 extra unit of charge per unit time. But like, let's just imagine like, well actually, yeah, you kind of have to imagine like 1 unit of charge. 1 extra unit of charge going around this circuit. And then if you think about how much energy is going to be lost to this internal resistance, it will be, because V is equal to IR, it will be equal to 1, because 1 is like the extra amount of current that you now have, multiplied by the small r, which is equal to small r. So basically what this gradient is equal to minus r thing is saying is that as the current going through this circuit increases by 1, you lose an extra minus r to this internal resistance as you go around. And so that's why the terminal PD is constantly dropping by minus r as you increase the current by 1, as you go from left to right in this graph. Okay, I hope that kind of made sense, but let me know if you have any questions or if this didn't make any sense at all, but hopefully it did. Anyways, like I feel like if you're IGCSE, you can still kind of understand this. Maybe you'll learn this in year 12 basically. If you're in year 13 but kind of forgot about this, then hopefully this was a good recap. Okay, I will also be holding classes for physics at IGCSE at A level, and also maths and further maths at IGCSE and A level. So DM and message Naproud at Naproud Academy if you guys are interested in any of those classes, which will be starting soon on August 5th. Okay, see you guys. Thank you.